Here we have a acid-base reaction, and we're being asked to identify both the Bronsted-Lowry and the conjugate acids and bases in the reaction. We also want to identify what the conjugate acid-base pairs are. So what we need to remember, our reaction is NH3 plus H2O reacts in equilibrium to become NH4 plus and OH minus. What we need to remember with this is that a acid is going to be a proton donor and a base is going to be a proton receptor. So whatever is giving away the hydrogen is going to be acting as our acid. So we're going to compare both sides of the reaction. We see that the NH3 is turning into NH4 plus. We see the H2O is becoming OH minus. So what that means is that we're having the water giving an hydrogen ion over to the ammonia, which is becoming NH4 plus. So that means that our Bronsted-Lowry acid is going to be our water, and our Bronsted-Lowry base is going to be the ammonia. Now, from that, we can also figure out what the conjugates are. The conjugate acid is always going to be paired with the Bronsted-Lowry base. So our conjugate acid here is going to be the NH4 plus. Our conjugate base is going to be the OH minus, because originally the NH3 was acting as a base. So when it turns into NH4 plus, it had gained a hydrogen, which it is now able to give away as well. And since giving away means you're acting as an acid, that's the conjugate acid. Same thing with the water too. In terms of our pairs, one conjugate acid-base pair is going to be the water and the OH minus. Helps if I spell correctly. And then, of course, the other one will be the other two chemicals. How do we know that these are conjugate acid-base pairs? They're conjugate acid-base pairs because they're basically the same chemical. They just have an H plus difference from each other. So the pair that starts as a base has one extra H plus in the products. The pair that is the acid in the reactants has one less H plus in the products. And you should remember as well that the acids don't always have a positive charge. The bases don't always have a negative charge too. You can have acids that have a negative charge. It's just that if it's a negative charge, it means that it is likely also an amphiprotic compound too. And likewise, we did this reaction with water. It does not have to involve water. We're using this particular example because this is applying the Bronsted-Lowry acid-base theory to what the Arrhenius acid-base theory could already explain in Chemistry 20. But we are in no way bound to this. You could have two completely different chemicals reacting with each other.